Biogas production from high solids anaerobic digestion. Anaerobic digestion is the process of breaking down organic matter through microorganisms in an oxygen-free environment. There are two resulting products from this process, biogas and organic matter. The produced biogas is a natural and clean replacement to the extraction and use of fossil fuels. At some point, biogas production either stalls or decreases during anaerobic digestion. Modeling the production of biogas is done to determine the ideal time to biogas ratio. Anaerobic digestion is considered high solids when the solid content is greater than 15%. To simplify the process, only the production of biogas was modeled. The resulting organic matter was not taken into account. The underlying equations in MATLAB code were written for a 100 meters cubed batch reactor at 48 degrees Celsius with assumed constant temperature. These decisions were made based on various reports and industry uses. Other parameters are chosen within the MATLAB code and can vary from one test to another.
This is the script file, and we first start off by giving the user a little information about what is happening, including some assumptions and what kind of reaction it is. And then we ask them to put in inputs for their time as well as certain concentrations. So it makes the program user-friendly and allows the user to be able to test different times and different concentrations. And then the code puts in the time and the concentrations into a function called ODE func2. And then that function file, as you can see, is here. We define a bunch of our parameters first off, and there's a good amount of them. And then we pull the initial concentrations that they defined in this part of the code. And then it runs through our reaction rates. So these are the growth rates of the bacteria, the death rates for the bacteria, hydrolysis, product rate, the degradation of substrates. And once the function has all those values, it goes down here, and has all the differential equations of the cells, the substrates, the product, and then puts them into a column matrix. Once it goes through this function, it goes back over here and runs through the ODE 45 function and spits out a matrix of concentration related to the time, and it looks a little something like this. And these are all of our different concentrations. And then it plots. So we are spitting out three figures, one plotting the cells, the other the substrate, and the final one the products. Once all that is complete, we find the location and the number where the maximum concentration is in the products figure. And then we spit out a message box that tells that. So now we're going to run the code. So it says, welcome, you are about to model the anaerobic digestion of high solids using a batch reactor. You will see another pop-up displaying the assumptions we are making. Are you ready to continue? So we're going to press yes. So these are the assumptions that they were talking about before. So the temperature in Celsius is 38. Our volume is in liters, which is 100,000. We're using a batch reactor, and we're inputting municipal solid waste. So now it is requesting the user to input a time. So we decided for our project that 720 hours would be an ideal time, which is equivalent to 30 days. And now we are going to get the request to put in initial concentrations. So we already picked these values ahead of time, but you can really put in any values that you want. So we did 0.5, 2.1, 1.9, and 0.89. So this is going to run and give us our figures. So our first figure is figure 1, and this shows our cells. We can see that they're all decreasing and will probably eventually hit 0. as time passes. So we can see here that the hydrogen in the acetogens lines are pretty similar, but we have the acetic acid line here that is going pretty quickly compared to the other two. This is because the conversion of organic acids is very rapid. So that is why the line decreases faster. For figure 2, we see the substrates. And again, we see the trend that they're all going towards zero as time passes. For the soluble substrate and the acetic substrate lines, they don't look like they're decreasing, but I promise you they are. And so is this line. You can see it starts from up here, the hydrolysis substrate, and shoots down towards zero. This makes sense because hydrolysis is our first step, so that is going to rapidly decrease. And then figure 3 is our products, and we are happy to see that it is increasing over time. And then it also, the next pop-up shows our max concentration, and at the time that is the max. So our concentration is 18.5, that is the max that we got, so of methane. And using the assumed theoretical values of biogas composition of 65% methane and 34% carbon dioxide, the concentration of the carbon dioxide will therefore be 9.67 if the biodigester is ran for 30 days.
This is important because we want to be able to maximize energy recovery of inputs to produce as much renewable energy as possible. So for our project, we're using municipal solid waste. So we want to be able to get as much energy out of it as possible by producing as much biogas. This is really important because in the world right now, this technology has been increasing significantly. And so we want to be able to understand this process and really maximize everything so that we can show that this is a really great technology since it is a green technology. As well as I work on a project called the USF Campus Food Waste Recovery Project, and it is taking dining hall food from campus and using it in anaerobic digesters to produce biogas. And fortunately, we were able to actually build some of the anaerobic digesters. So as you can see in the photo, there are the IBC tanks, and those are the actual digesters. And then in the other photo is some of my group members and for the project, and then also group members for this project who helped build them.